In the design of distributed network, the prevention of excessive voltage drop is a very serious issue. It set a limit to maximum feeder length, and different methods are placed to prevent or mitigate this voltage drop. The overvoltage have traditionally been a less concern here. If the voltage at the start of the medium voltage feeder is towards the upper limit of the permissible voltage range, then the risk of this overvoltage at a terminal of end user equipment would be very small. The introduction of distributed generation as a changed this, and the over voltage have become a more serious concern from now on, especially for location at some distance which are away from our main substation. The voltage rise is main limiting factor for connection of distributed generation. The maximum capacity of generation is about 2 to 3 megawatt on a feeder, and 8 megawatt on main 11 kV bus. The voltage rise due to injected active power is proportional to reactive part of the source impedance at a point of connection. For remote location, voltage rise can be significant. The amount of the active power needed for 1% voltage is calculated for a different feeder cross section, and the length is in section 5.2, that is in one of the reference paper. At 10 kV, 1.7% of voltage rise is obtained by connecting 1 megawatt of unit to an 5 kilometer from main bus along 50 mm square feeder. For 240 mm square feeder, the rise is only 0.4%. At a low voltage, the rather small units give significant voltage rise. Connecting a 10 kilowatt unit to a small 50 mm square feeder at 500 meter from the low voltage rather than the small units will give a significant amount of voltage rises. So when connecting a 10 kilowatt unit to a 50 mm feeder at a 500 meter from the distribution transformer, which may yields a 3% of voltage rise, so thereby the sizes will be much smaller. Then the load will be a maximum of the feeder, so the voltage rise will limit the amount of generation, so that can be connected only for a short feeder. The hosting capacity is set by the maximum load. The biggest voltage rise is obtained for a generator which is operating at unity power factor. The voltage rise is dependent on the fault level and the phase angle of the network impedance. The result here are summarized in one of the table. We will see in that further. For different X by R ratio and the low fault level. For high phase angle, the reactive power consumptions by a wind turbine will even result in some voltage drop. The hosting capacity here strongly dependent on the method which is used to prevent this under voltage. Using off-road load tap changes for the distribution transformer, which will give an high voltage magnitude during the load for a location which is far out along the feeder. This seriously restrict the amount of generation that can be connected. The hosting capacity becomes smaller or quickly when the generation is connected further along the feeder. For example, consider an 18 kilometer with a 10 kV capacity having 95 mm square with commonly used a design value. The fault level, the impact of this fault level and the phase angle of the source impedance on the voltage that is rising above towards 500 kilowatts wind turbine, which is represented in the following table. You can see hosting capacity should be low as 250 kilowatt for a generator which is connected towards the end of feeder, but the hosting capacity is strongly dependent on the number of design parameters, where when we consider this voltage limit as a biggest influence, so using a 110% of over voltage limit instead of this 108 will result in the hosting capacity which is almost equal to 1 megawatt towards the end of this feeder. The use of the shunt or series capacitor for voltage control will typically result in higher hosting capacity. So this also depends on our control algorithm which is used. When the capacitor banks are switched on the basis of this reactive power flow, so this may further deteriorate the over voltages. This regulators will detect the wrong detection when there is a reverse power flow in our power system. Tap changes are equipped with line drop compensation are also very less prone to this over voltage. With the presence of generator on one feeder will result in the voltage drop on other feeder. The risk of under voltage might even limit the amount of generation that can be connected to the network. So one of the simulations is considered, so that simulation result for a 230 volt low level voltage feeder. It has the total feeder length about 800 meters. The farthest point is 500 meters, which is away from our distribution transformer. So in this example, so the maximum load is 2.5 kilowatt, and the feeder impedance is 0.27 plus J 0.27 delta. It is expressed in the complex number. The results shows that the 90 kilowatt photovoltaic installation can still be connected at 350 meters from this distribution transformers, and that is actually before over voltage limit is reached 106%. A stochastic approach is used in the study as a deterministic approach would have resulted in a hosting capacity which will be equal to 65 kilowatts. The calculated voltage rise at the maximum production is 2.2% and 2.9% respectively in this example only. So measurement on 110 kilowatt site, however, shows the increase in the maximum voltage which is only 1.5%. So this is because the minimum load which occurs at different times of the day than the maximum production. So this signifies that the daily variation of both the load and the production should be included, otherwise the hosting capacity can be strongly underestimated. The potential voltage rise owing to the large number of photovoltaic panel connected to this low voltage has been calculated for the city of this UK, legislature city of this UK. So in the table what you are observing is a different phase angle for that 2 MVA, 5 MVA and 10 MVA and 50 MVA buses. For that if the phase angle is of 85%, then it will be a minus 12% for 2 MVA and minus 4% for 5 MVA and minus 2% for 10 MVA and minus 1% for 50 MVA. As if the phase angle is reduced to 70, for 2 MVA you can see that there is a significant reduce, that is reduced up to minus 3%, and for 5 MVA it is almost 0, and for 10 MVA it is 0, and for 50 MVA also 0. So if further phase angle is increased, so thereby you can see a significant amount of rise in the 2 MVA, that is of plus 6%, and 3% rise in 5 MVA, and only 2% rise in 10 MVA, and there is a 0% rise in 50 MVA. So if phase angle is further reduced up to 30% here you can see that there is a plus rise of 13% in for 2 MVA, and 6% rise for 5 MVA, and 3% rise for 10 MVA, and only 1% rise for 50 MVA. So if from this table we can conclude that if phase angle is less and the MVA is more, then you can reduce the source of impedance which is rising towards a 500 kVA wind turbine. So fault level can be reduced with a combination of minimum angle and maximum MVA. Here stochastic methods are used for calculating the load in every houses. A clear sunny day is used to give a worst case where the voltage rise is not typically a part. So in England, so about 50% of homes which are equipped with this solar power, each of them producing 2 kilowatt of power. So maximum voltage magnitude that rises from 250 to 254 volt within 110% over voltage limit. So this would be an unacceptable over voltage, although this occurs only for a small number of days per year, only for a few customers, that too only for few customers. Over voltage limit at 110% would set an hosting capacity up to 30% for homes, which is still a significant amount of penetration that on the same network we used to achieve. So which is used to study a micro CHP in combination with the solar power, only impact on average voltage, which shows from the study we can see that only 107% without generation, and 107.6 when 50% of home equipped with solar panel, and 107.5 when 100% of homes are equipped with this micro CHP. So there is only 107, but a small percentage, that to a fraction percentage change if we see this incorporating this micro CHP or the solar. So the voltage variation on low voltage feeder in Manchester, that is UK, which is supplying currently 69 homes, each of equipped with 1 kilowatt of CHP unit, micro CHP they are using. The feeder was specially designed to cope up with a large amount of distributed generation, and then 330 meter square cable was used as a precautionary measure instead of here 95 mm. Earlier they are using 95 mm, so now they are increased this 330 mm square. So this normally the measurement shows that load current are strongly unbalanced, and this unbalance increases towards the end of the feeder. the strongly unbalanced load increases with the risk of over voltage. So due to this distributed generation, the risk of under voltage will increase due to high load. And also considering that with small increase in the voltage along the feeder with maximum voltage that's been very close to 250 volt at the starter of feeder, and it's about 252 near the middle of the feeder, and at the end you see 253. There is a significant increase in 1 volt in every section. This could be a concern when the over voltage limit is of only 110% is used. So it should be noted that 95 mm square cable would give a voltage rise about 3 times the I. So this results in maximum voltage which is around 258 volts or 112%. So this increases in highest for a 10 minutes voltage magnitude where there is only 1 volt increase in all the 3 sections for a short duration. So if 95 mm cable is used, so the case would be different. Here it will produce 11.4 volts, almost 5%, which is unacceptable over voltage. This would likely caused from the using 95 mm square cable. A study of voltage rise along a 230 volts a low voltage network in Dublin in Ireland. So here the network which consists of number of feeders with a total of 3.1 kilometers which is of 3 phase, and 2.3 kilometers which is of single phase copper cable with a cross section 120 and 70 and 50 meter per square were considered. So here one of the cases is considered for a case study purpose, that too we see voltage rising in 230 volts in a low voltage network. So this is carried out in Dublin, Ireland, where the network consists of number of feeders with a total capacity here they defined is about 3.1 kilometers and 3.1 kilometers for 3 phase and 2.3 kilometers for single phase. So both the cables are of copper cable. So here the cross section of 3 phase, that is 3.1 kilometer, is 20 mm square, and the cross section of the single phase feeder, that is 2.3 kilometers, having 70 mm cross section, and another one cable with 50 meter square has been considered. So these networks are supplies 307 low voltage customers. You can imagine only in 3.1 kilometers this network supplies 307 low voltage customers. So here the minimum load is only a 0.1 per customers was assumed, but it is not a realistic value, but they are assuming 0.1 kilowatt. Mainly this type of supply is usually for lighting the houses. Okay, it is assumed to be 0.1 kilowatts of power, and they have considered this micro CHP was added to the network. So where maximum production is of 1.2 kilowatt. So at a power factor is 0.98, and here also the power factor is not accurate. They have assumed the power factor to be 0.98. For 100% of houses which are equipped with this micro generation, the maximum voltage during normal operation was 110.8% of the nominal value. So in this case what they have did is they have added a small micro CHP to the power network, where the maximum production of that micro CHP is of about 1.2 kilowatt, and he's also produced a power factor, but it is not an accurate value. It is assumed value, which is of 0.98 for some 100% of houses which are equipped with this micro generation. So the maximum voltage during the operation was found to be 110.8%, 110.8% of nominal value. So this is more or over like borderline of acceptability. Setting over voltage at 110% would significantly result in the hosting capacity between 62% and 100% per feeder. You can imagine per feeder 62 to 100% of hosting capacity. So during backup operation of this feeder, the feeder length is longer, which resulting in higher voltage rise. So the voltage magnitudes may up to 115.9% are possible. So during this backup operation, to keep the maximum voltage below 110%, even in backup operation, the hosting capacity should be as low as 23%.